Hi, I'm Christian Chapman-Bird from the Institute of Gravitational Research at the University of Glasgow, and I'm here to present our approach for rapid and accurate selection bias correction in extreme mass ratio and spiral population inference using neural network interpolators. So selection biases are present in most population studies because there are naturally forms of selection on what you observe compared to what actually occurs. And if you don't account for this, you can have biases in your results. So you must correct for this. So the selection function for extreme mass ratio and spirals is expensive to compute, primarily because the waveforms themselves are very expensive to compute. So we look to machine learning to try and speed things up and maintain accuracy without making any assumptions that will reduce sensitivity to important correlations in the EMRI parameter space. So extreme mass ratio and spirals are long-lived signals which consist of the inspiral of a stellar mass compact object into a massive black hole of on the order of millions of solar masses. These events are interesting for a number of reasons. Primarily for population inference, they are interesting because they offer very strong constraints on the parameters of the system. For example, the mass and spin of the primary black hole and the mass of the compact object that is inspiraling. The rates are somewhat uncertain because there are a number of astrophysical assumptions which are not well constrained at the moment, but we know that we expect that there should be at least a few, but up to a few thousand. So there's a range there, but importantly, there is enough to say that we could make some statement about the underlying population. So to give a brief refresher on population inference and how it works, we start with a population distribution, which we assume all of our events are drawn from. So the event parameters theta, and the shape of the underlying population is described by the hyperparameters lambda. So to begin with, let's say n events are drawn, each with their own parameters, and we immediately arrive at whether or not we detect those. If we don't detect them, then we don't see them for all intents and purposes. We don't know that they happened, and that's all we have. If we do detect them, then we can actually analyze them. So we can input them into parameter estimation. That gives us some information about the parameters for the individual events. That will give us sets of samples from the posterior from each event. So some subset of the original events, the detected ones, we have the information about their parameters. We can then input these into a second set of stage of parameter estimation, hyperparameter estimation, where we are specifically trying to infer the hyperparameters, lambda. So in the principle here, we assume that we have got the correct population model. As we're simulating everything here, we can assume that that's the case. It's another kind of a story for another time about whether or not knowing the right population, how much that will affect your results. And you end up with some samples of the hyperposterior. But these samples may, as I alluded to at the beginning, present a different picture than is true in reality, because there are some events there in the bottom left corner that we never got to see. They've gone in the bin. And we can only really recover an unbiased estimate by modeling that orange box there, the detection. So in our case, we're going to work with a simple population model that is somewhat astrophysically motivated, but is kept fairly simple for the purposes of demonstrating the approach. So we opt for a power law for the primary black hole mass with some exponent lambda m. Similarly, for the compact object, we also opt for a power law with some exponent lambda mu. And for the spin of the black hole, we opt for a truncated Gaussian with some mean and variance. And for a typical population sample, we obtain a posterior distribution that looks something like this. So for some parameters, we obtain very good estimates, but for others, for example, lambda mu in this case, the estimate is incredibly off. This is due to the fact that the compact object mass, in fact, does influence the detectability of the signals, which we can parameterize with the SNR to a great deal.
Sorry to interrupt. Just to let you know, you have a grey box to the right of your screen, which is covering some of the.
Oh, sorry. Let's try that. Is that better?
Yeah, that's perfect.
I can't really get rid of it. There we go. Okay. So yes. So the true value for lambda mu here is -2, but we cannot see it here. So how can we obtain a better result? So this is by considering the fact that the selection bias is the reason for our incorrect result. We can model this selection bias to try and reverse this effect. So in the absence of an actual EMRI detection pipeline, we can approximate detectability with an SNR threshold. So that is to say that if the SNR is greater than some threshold value, then we detect it, otherwise we don't. So this is probably the most simple detection model that you can produce, but it's a good starting point if you don't have an actual detection pipeline to work with. So the way that we actually perform this correction is by computing something known as the selection function, alpha. This is quite an expensive function to compute. In our simple case here, we can approximate this with a Monte Carlo integration, which is represented by this sum, where we draw sets of parameters from the population, and then we work out the detectability for each parameter, in our case, whether it's a 1 or a 0. This is just computing the SNR, as we saw on the previous slide, and then normalizing. So we're finding this mean value. And it takes a long time to, a lot of samples to approach a reasonable level of accuracy for this. So for example, here you can see that we need about 10 to the 4 trials to constrain alpha to within about 1%, which is quite expensive, especially if the SNR function is expensive as well. So in a typical hyperparameter estimation sampling run, we may need to evaluate this function 10 to the 5 times. And if the SNR function only takes a second to evaluate, then we're going to be doing this for years and years, which is not really practical. So we look to speeding things up a bit using some form of interpolation. So what we decide to work with, because more typical forms of interpolation, such as linear or cubic spline interpolation, do not perform well due to the high dimensionality of the EMRI parameter space, we train a neural network on this parameter space instead. So we generate EMRI SNRs and we train the neural network, which is a simple multi-layer perceptron, on this template bank. And the results are very accurate. In fact, we obtain errors on the order of 1% for the majority of the signals, which is more than sufficient for the level of accuracy you need to correct for the selection bias in this kind of study. So we end up with something, after running this with this selection bias correction, we obtain a posterior which has corrected for this bias, more or less. We also are able to estimate the rate of events. If there were to be no selection bias present, this is us essentially estimating the rate at which these events occur. This comes out in the maths for free as a result of us applying this correction. So we can see that our correction is more or less perfect. It's a really a great improvement on the original. But the cost is still quite high. So it's still costing about 0.1 seconds per likelihood call, which is significantly higher than in the case of ignoring the selection biases, as in the selection bias correction is bottlenecking this process. To avoid this, we train a second neural network on the selection function directly. So we sample the hyperparameter prior, and we train and generate some selection function estimates for those samples. We train a second neural network before sampling on those samples, and we obtain an interpolator that interpolates directly over the selection function. This is much, much more efficient and is a lot quicker, and we can obtain more or less identical results, but our likelihood call is now no longer bottlenecked and is roughly the same cost as in the uncorrected case. So yes, there we go. We have demonstrated that the SNR cut selection bias in EMRI population inference can be corrected for. In this simple case, I've been able to demonstrate, but also in more complicated examples. And this can be easily adapted for different choices of waveform model or population model. Just need to change your training data for the network. And as a more general statement, we've been able to show that complicated SNR functions like the extreme mass ratio and spiral selection function can be interpolated to a high level of accuracy at fairly low cost using multi-layer perceptrons. Thanks.
Thank you very much, Christian. That was really interesting. So we have one question from the chat. So it looks like your network is able to estimate SNRs less than 1 quite well. Shouldn't there be some sort of fundamental limit at which signals are essentially buried in noise and hence SNR estimation should fall? And how do you train in such low SNR regime? Okay,
so if we can head back to that. So I think I may have passed it actually. Yes. So let me get this, make this small again. What we're training on here is it's the optimal SNR. So this is a zero noise realization. So we train on the optimal SNR to capture the underlying SNR dependence for the parameters. And then when we are actually working with an actual population inference, we can convert this into a noise realized SNR by sampling from a non-central chi-squared distribution where the non-centrality parameter is the SNR. And in this way, you're right that essentially what you'll end up with is that the low SNRs will not be measured very well, but that isn't reflected here because this is a plot of the optimal SNR to demonstrate the underlying performance of the interpolator.
All right, thank you very much.